thank you for joining us today at this new session of the Nomadic Labs Research Seminar. Today we are being joined by Arthur Breitman and Steve Purcell, who are going to talk about the Checker project, Robocoin project. Let me introduce the speakers briefly before they start. Steve Purcell is a senior engineer at Tweag. He has worked in industry and open source for 25 years, leading engineering teams and projects all around the world. Arthur hardly needs introducing, but I'll do it anyway. Arthur Breitman is an architect of Tezos and previously worked in various companies, Google X and Waymo, and before that in other companies as well. Right, so let's start maybe, no? Yeah.
Okay. All right, can you all see the screen?
Yeah.
All right, so Checker, how to build Robocoins. And I'm not very good with graphics, so in order to make this a little less dry, I just added pictures of foxes on every slide. It's been a running joke inside of the team building Checker to just share fox pictures, and you'll see why. Okay, so definitions first. We've been talking about Robocoin. So what is a Robocoin? And I would like to say that I am aware that the name is lame. It's lame on purpose. So it's a cryptographic token, like you would have a cryptocurrency, but it controls its supply algorithmically by creating incentives for creation and destruction. And if you look at macroeconomics at supply and price, there's a dual of each other. And so either you can have a fixed supply and a varying price, or you can have a fixed price and a varying supply, or a combination of the two. And here we're trying to stabilize the price by using incentive for creation and destruction. So increasing or decreasing the supply. And Checker, that's a generic piece of software. So this is what we're building here. We're not building a coin. We're not building like anything like that. We're building a piece of software for people who want to create Robocoins. And so in this presentation, I'm going to call one of these hypothetical Robocoins a kit. And because the name kit also means a baby fox that created the whole fox theme. All right. So design goals. So what do we want to achieve here? The first is that we want to build a system that minimizes governance. They are systems for building stuff like Robocoins, like MakerDAO, for example, and they are extensively reliant on governance. Now, of course, governance is a big part of Tezos, and so I think it's a great tool to have in a toolbox. But whenever you can do something without governance, you should do it without governance. If you need governance, I don't think you should be afraid of using it. But here, I don't think we actually need that much governance, and so we're trying to minimize it. We want to minimize dependency on oracles. Oracles are very important for doing this type of systems very often, because you want to try to mimic some external index. But you want to be resilient as much as possible to oracle manipulation. Like your trust assumption about the oracle should be as weak as possible. You want to minimize the impact of liquidation. We'll see that there's a concept of liquidation in this protocol where you have some collateral, and if you don't follow the protocol, your collateral may be sold at an auction. And that can be very disrupting for people. Sometimes people have been liquidated in MakerDAO, for example, for no good reason, or in Compound, people have had bad liquidations happen. We want to minimize that. And we want to be built on sound economic principles. There's a lot of people trying to build this kind of things like basis, empty set dollars, which are based on fundamentally faulty economics. So we want standard classical economics behind this. What is not a design goal is to achieve a perfect peg between kits and some external assets. There's a lot of projects who say, oh, this will be pegged to exactly $1. I have a video on the topic, and this is essentially impossible. Unless you are tokenizing a bank account, you cannot build a Robocoin that will maintain a perfect peg to some other assets. If you do so, you violate some fundamental economic principles. So how does this work? So we are going to place Tez collateral inside a burrow. So the burrow, sometimes they're, in other projects, they've been called vaults. In MakerDAO, they were called CDPs. In some Tezos projects, they've been called ovens, like Colibri, for example. And out of this vault, we're going to mint kits. So you place your Tez, and then you can mint some amount of kits, limited by the value of the Tez that you put inside of this vault. And then we're going to have a target value for these kits. And we're going to have a drift, which affects this target. I'll go over this in detail. But generally speaking, if your kit is above your target, or if your target if you're missing your target, then we're going to decrease the drift. And if kit is below the target, we're going to increase the drift. And if your outstanding kit exceed the limit inside of a burrow, we'll liquidate the collateral. So I'll go over what these different steps mean, but that's a general algorithm for it. So first of all, the target, the drift, and the index. So the index is the price of something in kits, and it could be 1 Swiss franc, for example. So how much is how many kits can you buy with 1 Swiss franc? That's the concept of an index. It could be 1 cheeseburger. It could be anything. Any external index that you want. That can be what you're going to be targeting. And then you're going to have a quantity, and the quantity. Think of the quantity as being around 1 at the beginning, 1.0, but then it can fluctuate up and down. And the target is going to be the product of the index and the quantity. So an example of a target may be how many kits would it cost to buy a quantity Q of cheeseburger? So the index here is the cheeseburger, the quantity is Q, and the target is how many kits for a quantity Q of cheeseburger. And in general, we want the target to be close to 1. So if the target is below 1, it means essentially that kits are too expensive. It takes too few kits to buy Q cheeseburger. That's not what we want. And if it's above 1, kits are too cheap. If it takes more than 1 kit to buy Q cheeseburgers, then the kits are too cheap. So essentially, you can think of like Q cheeseburgers as what we want the value of 1 kit to be, what we want to be pegged at. And the reason I said we're not going to have a fixed peg is that if we had a fixed peg, then quantity would have to be 1.0 forever. Here, we're going to let quantity change. It's not always going to be 1.0. It can go up or it can go down. And so how do we know this index in the first place? So one thing we can do is we can rely on an oracle, and we can use a median of several oracles to get the value of the index. We can use an on-chain CFMM. So CFMM stands for Constant Formula Market Maker. This is the mechanism used in Uniswap on Ethereum, in Dexter, in KeepSwap. And that gives us an idea of the kit to guess price. So for example, if you have an oracle give you the XTZ-CHF time series, and you have an on-chain constant formula market maker who gives you the rate between kit and XTZ, you take the product and it gives you the rates between kit and CHF. So if you know that, and if you know your quantity, you can compute the target, and you can know if the target is above 1 or if it's below 1. And depending on that, you can adjust the drift. So what's with the drift? So the drift represents the rate at which the quantity changes. So it's a geometric change. So dq is the infinitesimal change in the quantity divided by q is drift times dt. So the drift might be 5% a year, for example. And if the drift is 5% a year, then on average every year, the drift is going to increase by 5%. Of course, it's not taken every year. It's taken every second. But annualized, it might be 5%. Annualized, it might be 2% or minus 3%. A positive drift means that the quantity increases over time. So it means that if your index is a cheeseburger and your drift is positive, it means that you want kits to be able to buy more and more and more cheeseburger as time passes on. If the drift is negative, it means that you expect kits to buy fewer and fewer cheeseburgers as time goes on. And the reason you have a drift is you want to balance out the demand for holding kits and the supply of kits. So how does this work? Well, so some people might want to hold kits. Why? Because it's convenient. It might be more convenient than holding a cryptocurrency, for example, which can have a lot of volatility. Or because it has a positive drift. If I have a positive drift, then it's better because I can buy more and more cheeseburgers, or I can buy more and more Swiss francs. So that would be a reason to hold kit. But you might even want to hold kit even if it has a negative drift, because it's just so convenient, because you're using it for payments, because you use it for stability. So really, it's possible for the drift to be negative. On the other hand, what is the supply? So the supply of the kit is anyone who creates a burrow and who issues a kit out of it. But of course, if I create a burrow and I issue kit, and then I put it back, and then I sell it, then I have to buy it back at some point. And so if I sell it to buy 1 cheeseburger, then maybe after a year, I need 1.05 cheeseburger to put it back inside my burrow and get my test back. So the drift basically balances out these two. And this is why you cannot have fundamentally an algorithmic type of Robocoin like the one I described without having a drift. In MakerDAO, they call the drift the stability fee, but it can only be positive. And it's necessary if you want your market to always clear that the drift can be negative, because sometimes there will be a large demand for holding the stable coin, so large that people don't mind if the drift is negative. And if that's the case, you want to be able to subsidize the people who issue the kits by having a negative drift. So how do we set it? Well, if kit is too expensive, decrease the drift. Again, so I should be, sorry, the paragraphs are inverted. So it should say a lower drift. If I decrease the drift, a lower drift makes it more attractive to mint and sell kits, so there will be a larger supply. And even, you know, if the kit gets if the drift gets negative, you could even subsidize minting. Likewise, if kit is too cheap, you increase the drift, and a higher drift makes it more attractive to hold kits and less attractive to mint and sell it. And that is going to balance, and that's why you can get kits to track its target. Liquidation. So that's the last part. If the collateral that you place behind kit or the Tez you place behind it is too low, then you can take some of this collateral and send it to an auction queue. And that queue basically processes Tez and sells them for auction against kits and burns the kits. What's nice is that we have a mechanism in Checkr that auctions can be canceled, which is quite important if you have an auction happening for a bad reason, for example. It could be a bad print in the Oracle, something like that. Auctions can be very, very disruptive for people. There were auctions in MakerDAO during March of last year, where the crypto markets crashed, and there were so many auctions on the chain, and the chain was so congested on Ethereum that some of these auctions went for zero. So you could buy people's collateral by paying exactly zero. You don't want that. There's generally a trade-off between how quickly you want to liquidate so that you don't take risk of the price moving away and the system becoming unbacked, versus how aggressive you want to be in funding, which can create congestion on the chain and which can create worse prices. And by and large, my attitude towards this is that it's better to be conservative. You're not actually going to be able to do something much better by trying to sell very, very quickly. So you're better off taking off your time and proceeding in an orderly fashion than trying to rush, especially with the trend of congestion on the chain. And I would say a good 50–60% of the work that is going in Checkr is making sure that liquidation and auctions are orderly. The last bit that I want to talk about is that there's a nonlinear filter around Oracle data. So whenever we get Oracle prices, you maintain a high prices and a high price and a low price. And the high price, basically, it accepts every upwards move as a ground truth, but it doesn't decrease by more than a certain amount per period of time. And the low price, again, it will accept any downward move, but it will not accept upward move above a certain rate. So they always converge back to the price. But the benefit of this is that if you have a crazy high price, someone comes in and gives a super high price for the Oracle, then it's not going to be reflected immediately. And we use a safe price for liquidation. That is, we're going to be conservative. We're going to assume the high price for liquidation, so that the Oracle needs to have been consistent for a long time in telling you that something needs to be liquidated before liquidation actually happens. All right, so that's a very short presentation. I really want to do mostly discussion with Steve and Q&A, but I thought it was helpful to give some general background before going into it so that we know what we're talking about.
Hi there. Yeah, thank you, Arthur. That was fantastic. I hope that that's completely clear and everybody understands everything about Checkr now.
Absolutely. I don't even know.
Not in any way overwhelmed.
I think we can wrap it now.
Exactly. Perfect. So, mic drop. I will just share my presentation over here. Fantastic. Okay, so yeah, I'm Steve Purcell from Tweag, and we're a remote software research and innovation lab. And three of us have been helping Nomadic Labs and Arthur with Checkr since October last year. None of us is particularly a Tezos expert, and I will just skip ahead to my next slide. Really, our goals have been generally to review and help refine Arthur's design for the various of the complex mechanisms inside Checkr, to determine the feasibility of actually implementing this on Tezos, given the technical limitations like the contract byte size limits and that sort of thing, and to guide the implementation and testing as we move towards actually being able to roll Checkr out for wider usage, and generally to help make Checkr a full, documented, and usable open source product that's trusted by the Tezos community. So the key challenges for us really have been complexity in a number of different areas. The The system itself is quite complex. There are a few interacting parts. So, as Arthur mentioned, there are auction mechanisms and borrowing and liquidation limits. And because there's a lot of data that covers a large number of people, and the parameters that control what those people can do, this ends up being a largely monolithic contract. So that's one key area of complexity. There's a lot of logical complexity in terms of getting fiddly calculations right and using the correct numbers, just the basics. There's algorithmic complexity as well because of handling the very large auctions in an orderly fashion, as Arthur alluded to. We do batching of liquidated chunks of collateral, batched into a particular size. We have to handle the auctions around that very efficiently. Then we have an AVL, which is a balanced binary tree, a self-balancing binary tree structure implemented then on top of big maps. So effectively, big maps end up being a malloc or free memory store for us. That all needs to be safe from memory leaks and not prone to excessive gas usage. Another challenge for us is the deployment target, so the bytecode size limits, as I mentioned, and we're targeting new Edo protocol features like tickets. So the deployment environment is a little bit of a moving target. And for security, obviously, that's an important concern for us, and there's a relatively large surface area for that as well. So we started on this in October, and we wanted to use code really to discuss and refine the design so that, well, I mean, we're software developers, of course we want to talk about code, but in order to unambiguously express what we were talking about, that was our preferred route. For that, we wanted to have a smooth development workflow and ideally use unit tests to capture rules and examples and some property tests where possible. So what we did was we wrote OCaml. We've got about 12,000 lines of OCaml now, excluding comments. And we did that because we had LIGO in mind as the deployment smart contract language. We structured the code into separate modules for the logical subsystems, like the two auctions and calculation of the parameters that govern the target and calculating the drift. And then we have a high-level checker module which pulls those all together and represents the API of the contract itself from a high level. So OCaml was a nice choice for that. We've been able to write unit and integration tests for the modules using OUnit 2, QCheck for property testing the invariance of various bits and pieces. And the development tools have been convenient. They've been the usual fast, correct tools like June, Merlin, and LSP. I guess the highlight in terms of technical achievements there would be the AVL tree, which itself is about 700 lines of code written by my friend, my colleague Utku. And that would be one area where we've done quite heavy property testing. And at the end of this phase, we essentially had the functionality of checker fully explored and implemented, and with some degree of testing. But of course, that's not the whole story, because that doesn't automatically translate to it working on Tezos. So the second phase, which has really been since about the beginning of this year, has been to address the challenges of actually getting checker onto Tezos. So really the goals there were to build a deployable contract and do things like measure the contract size and be able to benchmark gas usage and just understand if this thing will fly. And we didn't want to have to repeat all of the testing that we had done in the first phase, though, because we wrote tests partly with the goal of getting the code correct. Now, given our prototype was in OCaml and LIGO is a little bit different, the default plan here would have been to take the OCaml code and do a one-step, like a one-shot conversion through to LIGO, and then continue working with LIGO from thereafter. The issue with that is that we might make mistakes if we did that, so that behavior that we tested in OCaml might have been mistranslated and then be broken, and without unit tests in LIGO. And if we wanted to iterate a little bit on the design, then we'd have had to keep both versions maybe, or figure out how to change the design drastically after the translation to LIGO. So that wasn't really our preferred option. So in the Fox spirit, we came up with a cunning plan. I actually wrote this with Blackadder in mind, but foxes are cunning too. Hat tip to Arthur. So instead, we thought, well, actually, just how similar are OCaml and Caml LIGO? You probably know that LIGO has 3 different language syntaxes, and Caml LIGO looks very close to OCaml if you squint. Could we perhaps automatically translate our OCaml to LIGO as a build step? If we could, then this would let us keep our OCaml tests working and would give us valid LIGO out the other end. We'd be able to continue to iterate on the design in OCaml if we needed to, using the development and testing tools and the quick feedback cycle that you get with those. Well, if we could do this, that would be great, but it would need to be simple, because we didn't want to build another compiler so that it would go from OCaml through several compilers until it hits Michelson, because then you get several levels of impedance and terrible, terrible, terrible error messages. Well, we actually found a way to do this. First, we limit the OCaml syntax in our code to somewhat approach the slightly simpler syntax that LIGO has. So that means not using certain OCaml features like modules, non-tail recursion, for example. We can't use named function arguments. We have to ensure some degree of monomorphism, and sprinkle in some type declarations here or there. And then we've written some compatibility modules in OCaml corresponding to parts of the LIGO standard library, just the parts that we're using for now. So we have modules like LIGO.bigmap and LIGO.Tezos. We've got some simple wrappers for LIGO's built-in primitive types for nat and tez and their literal syntax, plus the operations on those, and a little bit of simple conditional pre-processing. So if I show you an example, and I have to thank my colleague Uku for making this example for me. Here is this is indicative of how we're doing checker. This is not the checker code itself. Our contract is slightly longer than this. But this is a silly contract that has an integer as its state, and you send it an integer. And if the integer you send is bigger than the state, then you get all of the contract's money, and it sets the new threshold. And if it's lower, then you lose your money. So just a silly example. So here you can see that we've got some prefixed identifiers for types like the LIGO.int. There's an operator there a few lines down. So LIGO.gt int is greater than int and int. Excuse me. And in general, this reads fairly naturally then from an OCaml point of view, and we can run unit tests. Excuse me. With our fantastic set of tools and adaptive libraries, we can then produce this camel LIGO automatically. So you can see the LIGO.gt int in the if condition has been converted to just gt int. That isn't built into LIGO, but we have some shim libraries there that allow us to do a little bit of compatibility from one to the other. Here is a preview of our advanced OCaml to LIGO compiler. It's mostly just a bunch of text replacements. So when I said that we didn't want to write a whole new compiler, this is what we were going for, just some fairly simple translations in the code. And here's an example of how we handle that gt int case. We do actually ship a little bit of additional LIGO along with our converted output. So it's almost like an additional prelude that we provide with the output code. And that, in this case, we get to use a name that is effectively an alias for the built-in greater than operator. So this avoids us having to worry about the different semantics of greater than with respect to different types on the OCaml side and on the LIGO side. And the box on the bottom there is the code that is only used on the OCaml side for some of the same things. So you can see that gt int there is aliased to the Z arithmetic library's GT function, because our internal representation of the LIGO int is from zarith. Cool. So the great news is that this approach actually works for all of Checker. We've been able to run all of that large chunk of OCaml code through and generate LIGO for it. It's quite a nice solution because you get compilation errors from OCaml or LIGO, depending on whether you get something wrong in the core logic or in the LIGO output. All of our tests still work locally. We've been able to deploy Checker locally. So we know that we're getting at least some degree of valid Michelson out of the far end. And that's all been quite encouraging. It's the things that we've done in order to achieve this, they haven't really been packaged up yet for general use because of some little impedance mismatches between the LIGO type system and the OCaml type system. There have been a few things that we've had to do for the translation that are quite specific to Checker and, for example, the different types of it, the tickets that we use internally. But for the longer term, it would be nice to wrap this up and share more information and possibly tooling to help other people use the same approach, because it's been quite productive for us. So in terms of the status on the implementation front right now, well, we still have some challenges. The large amount of OCaml code somewhat unsurprisingly translates into lots of Michelson bytecode. So currently we're at probably double the EDO bytecode limit of 32K. So we're exploring some strategies to cut that down. That might involve
16K. The limit is 16K. It might be 32K in Florence. There's a.
Oh, sorry. Okay, right. Yeah, I understood that the new limit was coming up. Yeah,
for time.
Exactly. But we're quite early in this process of actually having the large number that we can cut down. So there are a number of different options for doing that, including possibly simplifying some functionality. But there will be some core code structure approaches that will also make a big difference once we understand a little bit more about what's leading to the large output sizes. There are some tricks for keeping code in storage as well to circumvent the limits. So this isn't something that would be a blocker for the project, but all in all, we'd prefer to avoid doing anything too Wild West like that. So other than that, we're moving ahead to testing and wider review with all of this. And I imagine we'll be making more information publicly accessible soon as part of that effort. We've had lots of support and guidance along the way from Nomadic Labs. And yeah, particular thanks to Arthur and Joanna for helping us, for inviting us to help out on this project. And we'll be happy to answer questions now or via the Tezos Slack at some other time. But now is your chance to particularly ask Arthur.
Well, thanks a lot, Steve. Thanks, Arthur, for this talk. So, yeah, we're going to move on to the question session. I see in the chat some people already asked some questions. I'm going to read them aloud, I think. The first question is by Daniel, who asks whether you can explain the difference between an algorithmic stablecoin and a Robocoin.
Yeah, and so there's not a fixed terminology, and so people use algorithmic stablecoin to mean different things. So let's do the nomenclature. There's one thing which is for sure not an algorithmic stablecoin. It's a tokenized bank account. So you give some money to Circle USDC, and they give you a token, or you give some money to Tether, and they give you a token. You know, that's not algorithmic. It's very simple. You know, you tokenize a dollar bill or a euro bill like you would tokenize a like a stock or whatever. So that's fairly straightforward. It's mostly the difficulties around this are mostly compliance related and like interacting with the banking system. They're not really algorithmic difficulties. Hang on, let me restart my camera. And then you have everything else. So everything else is going to use an algorithm. So some people call everything else an algorithmic stablecoin. But I think the majority of people who say algorithmic stablecoins, they mean specifically one which is not collateralized. So they mean something which, there's only one coin. There's only like this coin which is supposed to be stable, and it's going to use some tricks to try to maintain a certain value without pegging itself to some external collateral. That does not work. Like that does not work. That's there's something called basis behind it. There's something called what's the name of it? Empty set dollar. All of these are going to zero. And there's pretty strong like financial and economics principle for why they don't work. And then you have the third category, which is it's collateralized, but it's collateralized by something different. So, you know, if you have a dollar collateralized by a dollar, in the first case, that's very easy. You have a dollar off-chain, a dollar on-chain. Simple. If you're trying to have something which is going to be close to the value of a cheeseburger, like I mentioned, or like a value of a Swiss franc, and but it's collateralized by something which is very volatile and which is different, then you're going to need an algorithm. And we've talked about this algorithm. So that's also algorithmic, but sometimes I say algorithmic stablecoin and people imagine, oh, you mean the stuff that's empty. And no, I don't mean that. So it really is three categories.
All right, thanks. Let's move on to the next question. Thibault asked whether it is expected to formally verify the checker contracts and specify them beforehand, I guess.
Yeah. So one of the work that I did with Steve, George, and the rest of the team, which was super helpful, is that I started out with like a pretty good idea of how checker works. But the first thing that I did was really go into the details and clean out every single corner case to get a really good spec. Now I'm not talking about yet about a spec at the level of a Cox specification, but something really, really detailed, like not just a hand-wavy explanation, certainly more detailed than the presentation that I gave. So we have a really, really good spec, which is in a good state for doing a Cox spec. I don't think doing a Cox spec of this, given the docs that we have, would be particularly hard. It's very well specified. Doing the proof, on the other hand, that's another matter. I would love for it to be verified. It may be a large endeavor, though. It would be fantastic if we can verify it, because it is a complex piece of code. Especially, Steve alluded to the AVL. The nice thing about the AVL is that you can do some model checking on it. It's something where you can capture bugs for a lot of fuzz testing, property-based testing will catch a lot of things for something like an AVL. But in general, like the rest of the logic, verifying it would go a long way. Yes.
I see. I can add something on that, on the question, I mean. Do the specifications that you have currently include aspects of the quantitative nature of checker, like the control mechanism? Do you
No, you can't really prove those because in order to prove those, you have to make some economic assumption. You would have to make some big macroeconomic assumption, and you can try to model that. And you're not, your result is only going to be as good as your approximation. So it's based on fairly robust. So it's a bang bang type of control. I didn't want so bang bang for those who don't do like control or you have two modes, like on or off. So we don't change the drift in proportion to how much you're deviating or anything like that, because it's really hard to come up with good coefficients that are not going to create oscillations. So instead of that, it's like if you're above, we start decreasing the drift. If you're below, we start increasing the drift. And all the parameters are set basically by thinking through a few cases by hand and making sure that the orders of magnitude are reasonable. But you can't really do much better than this. You could try to introduce more formalism, but I don't know. I don't think it will give you a more rigorous result.
All right, I see. Let's continue a bit. There are some remarks which are maybe relevant for you. I'm not going to read them. Ian asks a question still about the control mechanism. I don't know much about regulating dynamic system, but how the model compares to regulating systems like PID. In particular, is controlling the drift variation will make sense.
Yeah, so I mean, it would be fun to do a PID for drift. We have a much simpler controller. The problem with the PID for drift is that we would have no idea on how to set the parameters. If PIDs work well when you have a physical system and you can have extensive simulations. So you want to you want to do a self-driving car, you're going to have a PID system on like deciding how to turn, how to accelerate. That works really well. For an economic system like this, which is super messy, you wouldn't really have a way to set the parameters. I mean, you could have a governance layer and say, oh, we'll set the parameters of the PID based on what we observe. If we observe, if our system is over dampened, then we will like increase a little bit of proportionality constant. If we have oscillations, we'll decrease it. You could try to tweak it that way. There's a trade-off essentially between arbitrage, by the way, and the PID. So in some sense, if you expect the system to go to equilibrium, arbitrageurs can step in and put it at equilibrium because they speculate that the system will go back to equilibrium. So as a market maker, I can come in and expect equilibrium. So the difference between a system which is going to converge quickly to equilibrium by itself and one which doesn't is that it will cost more to the market makers. The market makers will need to absorb more supply. And so the funny thing is that you're not going to really observe it in terms of like the fluctuation of the price. You're going to observe it in terms of liquidity. You'll have, if your controller is working really well, you'll have more liquidity. If your controller is not working so well, then a lot of liquidity is, like a lot of the market maker supply is going to be soaking up excess demand, which is caused by the oscillation, and that will be translated as lower liquidity. So it's even hard to observe in some sense if you're not, converging fast enough.
Okay. Thanks. Let's move on to the next question. Still by Ian. Couldn't we implement this directly in Coq and then extract to LIGO camel? So this is for Steve, maybe. What do you think?
Potentially. It's not an avenue we explored. I haven't really looked into the viability of that, but it's an interesting idea.
Benjamin asks, is the lack of polymorphism in Michelson a problem for this specific contract?
No, I think we had a couple of little bits where we needed to tag some types, but I think maybe it was ticket related. But no, in general, it hasn't been problematic. Essentially, we're targeting LIGO as our output, and that's all quite regular and well behaved with regard to output to Michelson. So no.
I would say if we were using the AVL for two different things, like for example, if we were using the AVL for computing a running median, which is also an AVL type of problem, and for the auction, then it would be like annoying to have to redo the code. But since I would say there's not that much generic function that is used for many different things with many different types, so it's frustrating because you write an AVL, of course you want to write it in a polymorphic manner, right? It feels a little icky to write it with a specific type, but it's not an issue for this program.
Yeah, in order to target LIGO, we had to remove a bunch of polymorphism from the code. So that's an aesthetic compromise that you make, but
Okay. Nick asks, is the Robocoin less sensitive to speculators than other cryptocurrencies? More generally, what is the biggest benefit of keeping a constant target?
So, I mean, it could be for several different things. If you're targeting, for example, the cost of a cheeseburger, like you want your thing to be stable with respect to a cheeseburger, and maybe there'll be a drift. Maybe you'll buy one cheeseburger today, and the drift will be -2%, and you'll expect to buy 0.98 cheeseburger at the end of the year, or maybe it'll be +2%, and you expect to get 1.02 cheeseburger at the end of the year. The benefit is stability of purchasing power. So, let's say you want to enter a financial contract, long-term financial contract with someone on the blockchain. If you do it with a cryptocurrency, it's very, very volatile. So if I promise that I will pay you like 10 Tez for the next year every month, it could be a lot of money, or it could be little money, and then it's more. Whereas if you use something like kits, it's a lot more predictable. It's not completely predictable, but it should be a lot less volatile. So that would be one. That would be one interesting use case. So for payments, for units of accounts, for other things.
Okay. Let's take one last question, maybe. Jan asks, are you developing an attacker security model along the development of the contract itself?
Sorry, could you repeat that?
Are you developing an attacker/security model along the development of the contract itself? So maybe Jan can expand on his question if it's not clear.
No, sure, that's fine. That's something that's coming into scope for us now as we're moving towards the closer to Tezos end of the implementation. We have components in Checkr like a Uniswap facility, and we're very much aware of the fact that there's a lot of things that you can do wrong in producing a contract. And as we saw with some of the Dexter issues recently, we know that we have areas there that in Checkr that might need particular consideration with regard to security. So we're talking to a bunch of people from Nomadic Labs and beyond about all of those aspects.
Okay, thanks. All right. There was another question, but it was on the release date. So I guess the question is the answer is when it's done.
Well, there's release and release. So like I mentioned earlier, it's a piece of software, and it can be used by anyone who wants to build a Robocoin and so on and so forth can use this piece of software. So it's not so much about like when it's launched and when the piece of code is made available. And I think the reasonable thing to do is to make the piece of code available only once the development is a little further along, especially the testing is a lot further along, because you don't want an attractive nuisance. You don't want a piece of code that you haven't tested a lot, and then people like copy it and then launch something, and then there are tears. So I would say the first step is to really ensure to a large extent that it does what it's supposed to do, and that means more unit testing, getting the size down below the contract size limits, and also ideally some formal verification. I think it might be okay to just like release the source code before the full formal verification, so long as there's been extensive property, extensive testing and extensive unit testing. But it would be still nice to have a formal verification of the code base. One thing I'll mention, by the way, is about, and Steve, correct me if I'm wrong, I would say about 80% of the complexity of this is having an AVL for liquidation. And the AVL does, we could, instead of an AVL, we could use a list, which would be a lot simpler. The only thing the AVL gets you above a list is that if you get liquidated, and then the price recovers, and it's like, oh, maybe I don't need to be liquidated anymore, you can cancel. It doesn't have to be sent to auction. The benefit of this is that if someone manipulates the oracle, if there's a large swing and it just comes back, like some flash crack or something like this, you don't want to have a scenario where everyone gets liquidated. It's really nice to be able to cancel, to prevent like something bad from happening. So it's a really nice feature, but there is a very large cost in terms of like the complexity of the code, the amount of effort in development, the amount of places where bugs can happen, and the size. I think it would be a lot if you remove the auction, the size might be already under 32K or close to there.
Yeah, and there's clamping on the drift, partly to protect against significant swings in the oracle anyway. So it might be that that facility isn't as essential as it may sound at first.
Yeah, it could be.
Okay. Well, thank you very much. I think we don't have any more questions. I think we're going to finish the session now, if you're okay.
Okay.
Fantastic. Thanks, everyone.
Right. Well, thanks, everyone. Yeah.
Thank you.
Have a good night. Bye-bye.